You've used ChatGPT or Claude. You might use it every day. But here's what almost nobody actually understands. What is happening inside these systems when you send a message? Not the marketing version, the real mechanics. We're going to cover 10 concepts that actually explain how large language models work. Not metaphors, not analogies, the actual mechanisms, the things that determine what these models can and can't do. Start here. LLMs are not search engines. They're not databases. They don't retrieve information the way Google does. They predict text. Specifically, they predict the next most likely token given everything before it. That's the entire foundation. A token is not a word. It's a chunk of text, roughly 3 to 4 characters on average. The word tokenization is 2 tokens. A space before a word often counts as part of the adjacent token. An emoji is 1 token. This distinction matters more than most people realize. GPT-4 has a vocabulary of roughly 100,000 distinct tokens. Every word the model ever generates is selected from this list, 1 token at a time, based on a probability distribution over all 100,000 options. Because of tokenization, LLMs are famously bad at counting letters, reversing strings, and sometimes basic arithmetic. Not because they are unintelligent, because they never see individual characters at the input level. The structure of those problems is literally invisible to the model before any processing begins. In 2017, Google researchers published a paper called "Attention is All You Need." It introduced the transformer architecture. Everything you use today, GPT, Claude, Gemini, Llama, runs on this architecture. That one paper is the foundation of modern AI. Everything else is built on it. The core insight of transformers is attention. Every token in a sequence can attend to every other token simultaneously. The model learns which tokens are most relevant to which others. This is what lets it handle long-range relationships in text. Context from 10,000 tokens ago can still influence the current token. Pre-training is where the model gets its base knowledge. You take a massive corpus, Common Crawl, books, Wikipedia, GitHub code repositories, and train the model to predict the next token billions of times across trillions of examples. No labels, no human supervision. Just predict what comes next, get a gradient update, repeat. At enough scale, something interesting happens. Models trained only to predict text spontaneously develop abilities the training objective never explicitly required: translation, logical reasoning, coding, arithmetic. This is called emergence. The research community does not fully understand why scaling causes it. It just does. GPT-4 is estimated to have trained on approximately 1.8 trillion tokens. That's roughly equivalent to 13 trillion words, textbooks, websites, code repositories, scientific papers, books, everything. The model's knowledge is a compressed statistical representation of that corpus. Parameters are the model's weights, numerical values adjusted during training to minimize prediction error. A 70 billion parameter model has 70 billion such numbers. They collectively encode everything the model knows about language and the world, but they are not a database. You can't query a specific parameter and get a fact out. Fine-tuning takes a pre-trained model and specializes it. You provide examples of the specific behavior you want, answering questions helpfully, refusing harmful requests, following formatting conventions, and continue training on those examples. The base model gets shaped into an assistant through this process. RLHF stands for reinforcement learning from human feedback. Human raters compare 2 model outputs and indicate which is better. A separate reward model learns from those comparisons. The LLM is then trained using reinforcement learning to produce outputs the reward model rates highly. This is the primary mechanism by which helpfulness gets baked into models. To give you a sense of scale, Llama 3 from Meta has 70 billion parameters in its largest open version. GPT-4 is estimated at over 1 trillion. More parameters generally means more capacity, but also proportionally more compute required to run inference. A trillion-parameter model doesn't run on your laptop. Constitutional AI is Anthropic's approach to alignment. Instead of relying exclusively on human feedback, The model critiques its own outputs against a written set of principles, then revises. This reduces dependence on human reviewers for every response and creates more consistent behavior. The values are embedded through training, not applied as a runtime filter. When you send a message, inference works like this. The model runs a forward pass through all its transformer layers, produces a probability distribution over its entire vocabulary, samples one token from that distribution, appends it to the sequence, and runs the forward pass again. That loop, repeated hundreds or thousands of times, is what you see as streaming text. Temperature is a parameter that controls how the token sampling works. Temperature 0 always picks the single most likely token, completely deterministic, but tends to be repetitive. Higher temperature gives low probability tokens a chance to be selected, more varied and creative, but at high values starts to produce incoherence. Most production systems run between 0.6 and 1. Hallucination is not a bug that will eventually be patched out. It's a structural consequence of how these models were trained. The training objective was to predict plausible text, not to verify truth. When the model doesn't know something, it doesn't have a circuit that returns uncertainty. It generates the most statistically plausible sounding continuation. That's what hallucination is. The reason it sounds so confident when it's wrong. Confident text is more common in training data than hedged text. Academic papers, textbooks, news articles, they assert things with authority. The model learned that tone. Calibrating uncertainty, knowing when to say I don't know, is an active research problem. It is not solved. Gemini 1.5 Pro has a context window of over 1 million tokens. That's roughly 750,000 words, approximately 10 full novels the model can attend to simultaneously. 2 years ago, most models had context windows of 4,000 tokens. This has been one of the fastest moving areas in the field. The context window is the model's working memory. Everything inside, it can influence every generated token. Everything outside, it effectively doesn't exist for the model. The KV cache stores computed attention values from previous tokens, so the model doesn't have to reprocess the entire context from scratch on every generation step. That's what makes token-by-token generation feasible. Why are LLMs unreliable at multi-step arithmetic? Because arithmetic requires exact symbolic computation, not statistical pattern matching. LLMs are pattern matchers. They've seen enough math and training data to get common problems right by approximation. The real fix is tool use. When a model calls a calculator or code interpreter instead of generating the answer itself. Chain of thought prompting works because it gives the model space to generate intermediate reasoning tokens before reaching the final answer. When you say think step by step, you're not activating a reasoning module. You're letting the model build up a sequence of tokens that serve as scaffolding. Each intermediate token improves the probability of the correct final token. Reasoning models like O3 and Claude's extended thinking mode take this further. They generate thousands of internal reasoning tokens before producing a response, sometimes 10,000 or more. Whether that constitutes thinking in any meaningful sense is genuinely contested among the researchers building these systems. What is not contested? It produces substantially better results on hard problems. What LLMs actually cannot do reliably: retrieve specific facts without retrieval augmentation, perform exact arithmetic without tools, update their knowledge after training ends, or detect when their own outputs are wrong. What they can do: comprehension, generation, summarization, synthesis, translation, code explanation, they do extraordinarily well. The failure modes are just as specific as the capabilities. Here's the honest summary. Large language models are statistical pattern engines operating at enormous scale. They are not thinking the way you think. They are not retrieving the way a search engine retrieves. But the line between very sophisticated pattern matching and something that deserves a different word is genuinely contested, even among the people building them. New AI lesson every day. If this breakdown was useful, subscribe. There is a lot more coming and you don't want to catch up later.